It. I can take a picture of it and draw it. Okay. Kind of learned last session how to figure out domain algebraically based on the function. I want to talk about it now based on the appearance of the graph. There's hard ways to do domain and there's easy ways to do domain and range. And domain, the easiest way tends to be to work on the function, the algebraic function. Whereas with range, a lot of times it's easier to see range from a graph. Okay? Let's take this function that we talked about last time. If you recognize that as the square root function, you know it starts right there and it goes like that. Now, we figured out what's the domain again? Tell me. Doing it algebraically, looking at the function. What are the possible values of x?
Oh, it's no negative numbers.
So if we define it, it's x is greater than or equal to 0. Has to be. Okay? And if you look at the graph, that's what the graph is telling us also. In other words, when you're looking at domain, you want to be looking horizontally. You want to know, are there any values of x? Can I go all the way out in this direction? In other words, can I go to positive infinity? And the answer is yes. Can I go this direction? No. I don't see any points on that graph that go to the left of the y-axis. Okay? Now, let's talk about range. Range is what the vertical, what the y numbers can be. So when we're looking at range, we want to have our eyes be looking vertically. And this is tough for a lot of people, this business of looking horizontally or looking vertically. It's hard not to just look at that graph, but that's not really what we're concerned with. We're concerned with, does this thing go all the way up to positive infinity on the vertical axis? We can see that there are no points on the graph that go in this direction. So there's no way y can be negative. Question is does this thing keep going up as x goes to the right? What's the answer?
No.
Actually, it does. In other words, it's hard to see because I've drawn it so that it looks like it kind of flattens out, right?
Yeah.
But it really doesn't. If you look at the graph in combination with the function, well, we can see that if I took the square root of 100, it would be 10. If I took the square root of 10,000, it would be 100. If I took the square root of 1,000,000, it would be 1,000. In other words, by choosing a value for x that's just large enough, I can keep making y get bigger. And it never stops. It keeps going. This really does go all the way to infinity, even though the graph is a little bit confusing. So the range here is the same as the domain. Y has to be greater than or equal to 0. And we can figure that out. For this function, it's almost easier to figure it out algebraically as opposed to graphically. But I want you to be able to do it graphically also. Let's take another function. This one. Y equals 1 over x. Okay? again, we could probably figure out algebraically what values for x can we put in. But let's graph the function and see if we can see it visually. This is a hyperbolic function, is what it's called. Okay? And what's happening with a hyperbolic function is this function is getting closer and closer to the y-axis the smaller and smaller x gets, or the closer x gets to 0, right? And on this end over here, the further to the right we go, in other words, the bigger and bigger x is, the smaller and smaller y is. Think about it. When x is 10, y is 1/10. When x is 100, y is 1/100th. In other words, y really is getting smaller and smaller and smaller. Now, let's look at domain. Remember what the domain was in this function? Remember, when you're thinking about domain and you're trying to do it algebraically, try to figure out what x cannot be. Is there anything x cannot be?
0.
Okay, anything else? That's true. It cannot be 0 for sure, because you cannot divide by 0. Can x be a negative number?
Yes.
Can x be a positive number?
Yes.
Can x be a fraction?
Yes.
Fractional number. So it would appear that x can be anything except 0. Now let's look at the graph. Well, if we're looking horizontally and we go in that direction, we can see this graph, even though I haven't I really need to put arrows on it like that, because that's what says that it continues on in this direction. Doesn't come to a stop where I drew it. But if we look to the left, we can see that x can be any negative number you want, right? In other words, here x might be -1, there x is -2, there x is -4. I keep going, x could be -1,000,000,000. Okay? Now, if we look to the right, we're trying to figure out domain. So we're having our eyes look left and right, not up and down, left and right. And we can also see that I can find values of x, all positive numbers are going to be on that line. Now, what we have, are you familiar with the term asymptote?
No.
Okay, an asymptote, this is a vertical asymptote. If you have a vertical asymptote, the graph cannot cross it. And I've already decided that there's x can't be 0. Well, that's wherever your denominator is 0, that's where you have a vertical asymptote. Okay? And there's a horizontal asymptote also in this function at y equals 0. And you'll notice that y does the same thing. Y never hits that horizontal asymptote. It just approaches it. As you go in one direction or the other, either towards negative infinity on the horizontal axis, or positive infinity, y can be any value you want except 0. There is no way to make y 0. What possible value could you plug in for x that would make y 0? The only way a function is equal to 0 is if its numerator can be 0. This numerator is a fixed 1. So there's no way y can be 0. Okay? So, tell me what the domain is. And you can describe it however you want.
The domain is anything greater than 0
or
or
less
less
than
than
0.
0.
Yeah, the most efficient way to write that is all real numbers except x not equal to 0. In other words, if there's only one value that x can't be, then this is a good way to write it. Because the complicated way to write it would be minus infinity up to 0 with a parentheses because it can't be 0 in combination with 0 to plus infinity. That is the official way of writing domains and ranges, especially if there's more than one interval. In other words, in this case, we don't have a continuous interval. We have this interval where x can go from minus infinity to 0, but it can't be 0, combined with this interval where it can go from 0 to infinity, but it can't be 0 again. This says, these two lines say the same thing. Now, what's range? If you don't know the answer, look at the graph and see if you can figure it out from the graph.
Anything greater or less than 0 again, so the same one, all real numbers except 0.
Okay? All right. Now, we won't get too complicated into this. I don't want to spend all of our time on domain and range, but let's just take a couple of other examples. Now, what's the domain?
All real numbers except
What can't x be? What would cause division by 0?
1 less than 1.
No, exactly 1. X can be anything in the world except 1, because only 1 is going to cause division by 0. No other value of x makes this denominator 0. Okay? So it's not always x equals 0 when it's in the denominator. It's whatever makes the denominator 0. In other words, if I make this even more complicated, where I say 1 over x minus 1 times x plus 2, now what's the domain?
Um,
I'm going to give you a hint. There are two values of x that would cause that denominator to be 0. Notice that if either of these is 0, then the entire denominator is going to be 0, because 0 times anything is 0. So I got two values that x can't be. What are they?
0 and
No, x can be 0. If x were 0, this would be minus 1 times 2, which would be minus 2, and I would have 1 divided by minus 2. Nothing wrong with that. What value makes that 0?
1.
Okay, that can't be 1. And what value makes that 0?
-2.
Yeah. So here's a function where the domain's a little more complicated. It's still almost all real numbers, but there are two values that x can't be. All right. Let's talk about quadratics, because these are the ones where it really is much easier to figure out range from the graph than it is the quadratic. Just take the most basic function. What's this called? The graph of that? Remember? The graph of a quadratic?
Parabola.
Okay. And this particular parabola has its vertex at 0, 0. You can tell if you plug in 0 for x, you get 0 for y. Now, all quadratics, pretty much, as long as they're not in the denominator, all quadratics have a domain of all real numbers. And you can see that. In other words, if I look in that direction, I can tell that I can plug in any value I want for x. And if I look in that direction, I can plug in any value I want for x. And I can also plug in 0 for x. So the domain is all reals, with no exceptions. What's the range? And this time, look at only the graph, but look at it vertically. What are the allowable y values?
Anything greater or equal to 0?
Yeah, y greater than or equal to 0, and you can understand that, right? Because no matter what value I put in for x, if I put in a negative number for x, well, when I square it, it turns positive. So even all negative numbers for x give you positive y's. The lowest that y can be is 0. So this is the range, and you can see it from the graph. And I'm also going to write this one in interval notation because it's kind of interesting in interval notation. You don't use parentheses. You use a bracket. The difference between a bracket and parentheses is that a bracket says that it can be 0. If I used a parentheses, well, then 0 wouldn't be allowed. So I can't use parentheses. I use bracket when that number can be allowed. I use parentheses when it can't be, but you can go right up next to it. Now, you always use parentheses around infinities. You never use a bracket on infinity because infinity is not a number. It's a concept. It's growth without bound is the way it's defined. It is not a number. It's not proper to think of it as being a number. Okay. Now let's go back and talk a little bit more about vertex format, intercept format, and standard format. Because I think I didn't really make myself clear enough on this. First of all, if I give you a function that is in vertex format, which is, you should remember vertex formats. In other words, vertex format over here is y equals some number times x minus another number squared plus k. So when you see a quadratic in that format, it's going to look something like I've drawn over here. Okay? Now, if I multiply this out, I mean, you can always multiply it out, right? So I get this. Square what's in the parentheses, which is x minus 3 times x minus 3, which gives me that. And then I add that 4. And I distribute everything, and I get this. Plus 18 plus 4 gives me plus 22. Okay? So these two are the same. The only difference is this is vertex format, and this is standard format. They're the same function, and they're the same quadratic, and they're the same graph. It's just I've got them in different formats. Okay? And I can do the same thing with intercept format. Remember what intercept format is. It's y equals some number. This time I use x minus p and times x minus q, where q and p are the intercepts. I don't use h and k, which are the coordinates of the vertex. That's why it's called vertex format. This is intercept format because it's showing me the intercepts. And an example of this might be 2 times x minus 6 times x minus, let's make it 4. Okay? Now, again, what this tells me directly is that my x-intercepts are at 6 and 4. In other words, your x-intercepts are what makes that 0 and that 0. Notice that, again, the x-intercepts are where y equals 0. Well, if I put in a 0 for y here, the only way that y can be 0 is if this term is 0 and that term is 0. So that gives you your intercepts. Okay, and you can draw a pretty good graph with just the intercepts. So this is a valuable format, but again, I could take this and multiply it out and get it into standard format. If I multiply these two binomials together, I get x squared minus 4x minus 6x, so that's minus 10x plus 24. Now if I distribute, I get this. Again, these two are the same. You can see the advantages of the top one though. The bottom one, I don't know really how to graph that very well. In other words, the bottom one doesn't give me the vertex, doesn't give me the x-intercepts. I've got to do more math to figure it out. And there is a formula for figuring out the x-intercept of the vertex when it's in standard format. And we'll go over that shortly. But the main reason I'm going through this explanation is many times you'll get it in this format, standard format. And the easiest way to graph it is to try to unmultiply it together. It's a little like factoring to get it into vertex format. I don't know how to graph this, but this one up here, the same thing, I know exactly how to graph it. The vertex is at 3, 4, and it's a parabola that opens up. Done. So there's a technique for getting it from standard format into vertex format. And that technique is called completing the squares. And it's not in this section, but I happen to be looking for in the next section, and that is something they want you to know how to do. So I figured I'd kind of mention the concept of it now. We won't go through it tonight, but completing the square is what allows you to take it from standard format and put it in vertex format. Okay? Not so easy to convert standard format to intercept format, but of the three of these, the most valuable one is vertex format. And that's why they listed it first. Vertex format first. Intercept format second. And notice they don't even mention standard format. The problem is that you get most of your quadratics in standard format. So you've got to do some things to be able to figure out how to graph it when it's in standard format. Now, what are we looking at time-wise? 7:30. Let's go a few more minutes. You started 5 minutes late. Is that okay?
Yeah.
Okay. let's look at some of these other concepts here. Minimum and maximum value. When they talk, oops, I got to take a picture of this again. When they talk about minimum and maximum values, they're generally talking about parabolas. Okay? If I have a parabola that looks like this, where this vertex is at 3, 2, what's the minimum value of that function? They're asking about the y value. What's the lowest value of y on that parabola?
2.
Okay, that's the minimum value. In other words, you would say that there is a minimum on this parabola, and it comes when x is equal to 3 and its value is 2. You with me? A lot of this is just kind of terminology. Now, let's say that that thing is reversed, goes through the same vertex, but it's negative. It goes down instead of up. Does this function have a minimum value?
It's still
No. No. Notice that it's headed towards negative infinity on the y-axis, both sides of it. So there is no minimum value for this function. But what is there?
a maximum.
Yeah, that right there is a maximum value. That because of the way I did it, it happens to come at the same point, and it comes, and the way you define these, you want to differentiate between what they're asking for here. When they're asking for minimums or maximum values, usually they're asking what the y value is. If there's a minimum, what is it on the y-axis? But it's best to give it as 2 points. In other words, this maximum comes when x is 3 and the value of the maximum is 2. So when they're talking minimums and maximums, they're generally talking, for Algebra 1, they're always talking about quadratics. Notice that linear functions, if I just draw a straight line like that, and it goes on forever to there, and it goes on forever in that direction, does this have a minimum value?
Yes.
Where?
Wait, no.
No, it doesn't. It goes to infinity. It goes to infinity it goes to negative infinity in the x direction, and it also goes to negative infinity in the y direction. Again, think about reading graphs as looking at it horizontally for domain and then looking at it vertically for range. Does it have a maximum value?
No.
Nope, it doesn't. So linear functions never have minimums or maximums. So when they're talking about minimums and maximums in Algebra 1, they're always talking about parabolas, because parabolas always do have a minimum or a maximum. Parabola looks like that, there's the minimum. Parabola looks like that, there's the maximum. Okay? And it comes always at the vertex. That's why vertex comes ahead of minimum and maximum, and why it's so important is because that vertex gives you the minimum and maximum, but it doesn't tell you what it is. You have to look at the graph to know what it is. In other words, when the parabola opens up, you're looking at a minimum. When the parabola opens down, you're looking at a maximum. Axis of symmetry is just the imaginary dotted line that goes through the vertex and the parabola is symmetrical on either side of that dotted line. That's what axis of symmetry is. So in our case, where that point came at 3, 2, it's the axis of symmetry. Remember, it's a line. It is not a point. It is a line. What's the equation of that dotted line? Vertical lines are always x equals some number. What's the number here?
X equals
It's the x
3.
value. Yeah, that's the equation of that dotted line. If I wanted an equation of a horizontal line, say that line there that goes through the point -4, the equation of a horizontal line is y equals some number. So vertical lines are always x equals some number, no y. In other words, it's just x equal 3, and the horizontal one is just y equals -4. Whatever point they're going through is the number that gets put in there. All right. Tell me again what your graphing calculator situation is. We're not going to go through this. I just want to know for next session if you have one.
I unfortunately don't have one yet.
Okay. Have you found out? I was on Chatfield's site the other day, and I remember reading that all math students must have an Inspire. Now, you don't have an Inspire yet, right?
No, I don't.
Okay, so we won't cover this subject then. Once you get your Inspire, let's talk a bit again about how to use it. And it's possible that, do you have a TI-84? Or do you have a sibling that has a TI-84?
I can ask my stepbrother.
Okay. It may be that Chatfield will allow you to use the TI-84, which is an older version of a calculator. It's not as good as the Inspire, and the operation of it is quite different. There's quite a learning curve. So you don't want to have to deal with both calculators. So if at some point in the next 4 years, you're going to need an Inspire. I'd bet money on it.
Yeah.
So you've got to go out and get a calculator, get the Inspire, don't get the TI-84.
Okay.
And they're about the same cost. In fact, I don't know. The Inspire, I think, is like $125, and there's probably a student rate where they'll make it even cheaper for you. But that's what you'll want to get. And you can wait until you have one day of math class where they tell you for sure that you got to have that.
Okay.
Just make sure you don't wait too long, because I'm sure there's going to be lots of students all over town that go immediately to the store after their first math class to buy an Inspire.
Yeah.
So there might be some difficulty with supplies if you wait too long. But anyway, we'll be done with, oh no, we still got a few more items under this middle topic here that we'll pick up on next time on Wednesday night. Okay?
Sounds good.
All right, Phoebe, have a good next few days.
Yeah. See you on Wednesday.